Okay guys, so in this lecture we're going to be learning about bright line spectra, which have another name. They're also called emission spectra. And it has basically three steps. It starts with energy absorption, followed by the energy emission, and then thirdly, it's just how do you break that up into a bright line spectrum. We'll even learn how to interpret them a little bit today. There's a classwork associated with this lecture. You can copy it down now. You need to do a little bit of reading in class, and we'll answer questions 27 and 28 on page 11 without explanations because they're very, very simple. We'll have some Unit 1 note cards as well, and all of that is due on Monday because we'll be getting ready for our exam, which will be early in the week. So for your do now, please copy this down into classwork. These 4 questions, don't solve them yet, and the aim is what are bright line or emission spectra. Alright, so step 1 is the energy absorption step, and you can put this in your Cornell notes. So in the diagram to the left, it's not animated here, but I can show it to you in class tomorrow. What's going to be happening is that the atom is absorbing energy from an outside source. So I just went ahead and wrote that in for you. Now, one lucky electron will be the recipient of all of that energy, and when it receives that energy, it's going to move up a level. The reason for that is because higher energy levels contain electrons with more energy. So if the electron absorbs energy, it's going to move to a higher energy level. Now, when that electron moves up to a higher energy level, it is considered to be in an excited state. And for clarity, an excited state just means that you are in an energy level above the one that you would be in if you were in ground state. And if there is ever a question about what ground state is, remember, check your periodic table. The periodic table lists the ground states for all elements. So if you want to see this animated tomorrow, I can show it to you. But basically, we're going to draw in the new electron configuration for the atom once one of the electrons absorbs energy. So right now, they're both still in ground state, but I'm just going to put in a little arrow that shows one of them moving up to a higher orbital. And I'll just cross this one out down here. It's not going to be there anymore. So when this atom was in its ground state, its electron configuration was simply 2. But here it is in its excited state, and its electron configuration is 1, 1, indicating that it has 1 electron in orbit 1 and 1 electron in orbit 2. The second step of this process, called excitation, is called energy emission. So the second step after absorption is energy emission. So both of these electrons have the ability to move to a lower energy level because both of the electrons in these two diagrams are sitting above ground state. They're in an excited state. So that means they're both in excited state, and predict what will happen to each electron by drawing an arrow indicating the direction of its movement. I'll draw that in a second, but you should press pause right now and think about what's going to happen to both of those two electrons as they return to ground state. Alright, so I drew in my answers. I have the first electron going down 2 orbits to orbit 1, and the second electron is going down 1 orbit to orbit 1. Which of these excited electrons would release more energy? I think it's relatively clear that the one that would release more energy is the one that falls the most number of levels. So that's going to be the atom on the left. And it's going to, in short, it's going to release more energy because the electron had to absorb more energy to get to the higher energy level. So it's going to release all that energy on the way down. This guy had to absorb less energy to get here, and so it's going to release less energy to get there. So step 3 is the bright line spectrum step. So in this third step, after the electron has absorbed energy and moved up a level, it's going to release energy as it moves down a level, and the way that it releases that energy is in the form of light. And this is where our bright line spectra come from. And we have like this glow of energy coming out to represent that process. So when electrons go from an excited state to the ground state, they release energy. In what form is this energy released? That form is going to be light of a specific color. What would you observe if the excited electron falls from a higher energy level? So if it falls from a higher level rather than a lower level, you might observe something different. So what I would say is that you're going to observe a higher energy color of light. Examples of high energy colors of light are colors like violet, purple, and blue, even green. And then lower energy level colors are ones like red and yellow. Those have lower energy, and then the ones over here on the right are higher energy. So there are so many different colors of light that we tend to think of them all as separate, but they aren't. So light, even white light, is actually a mixture of a few basic colors of light. So we can separate the mixtures of light from any sample using a spectroscope. The result is a series of colored bands representing the makeup of light in that sample. So when we do these electron excitation studies and they release this color of light, we try to acknowledge that that color of light that it's releasing is probably a mixture of colors. So we run that light through a device called a spectroscope, and it separates that light into a mixture of colors. So let's say, for instance, that what you see up here, releasing this sort of nice yellow color, this golden color, let's say it's helium. And it's going to release this nice golden color. We know that that golden color has more than one color inside it, so we run it through a spectroscope, and the spectroscope spits out this nice little evenly organized and divided graph that shows all the different colors that are inside that golden color. And since it's so specific and so organized and so separated, then we can think of this as like a fingerprint for helium, because all of these different bands are representing electrons that are falling back to ground state. Each one of these bands represents an electron falling down to ground state. The purple bands represent electrons that are falling a long way, and the red bands represent electrons that are falling a shorter distance. Because if you fall a shorter distance, you're releasing less energy, that's red. And if you fall a longer distance, you release more energy, and that's purple. So, and in between you have the other colors. So that's the long and the short of bright line spectra. So just keep in mind on this slide, you should add to your Cornell notes that every element has a different bright line spectrum. That's what this is. And that's a result of differences in their electron configurations. So we can interpret bright line spectra as well. Firstly, how can bright line spectra be used to identify the elements in a sample of atoms with excited electrons? What I would say is actually quite simple. Just make sure that you compare the bright line spectrum of the sample of atoms. Just compare it to bright line spectra that you already know. If you find a match between the bright line spectrum of what you're studying and the bright line spectrum of an element that you already knew, if you find a match, then you found the identity of that element. So what I wrote down here was just compare it to a known spectrum. That's what the regents are going to want you to say at different points. Another question, what would the bright line spectrum of a sample of atoms of hydrogen and helium look like? So what I'm getting at here is that you have two different elements in the sample, and each element has its own bright line spectrum. That's what sort of makes this answer possible, but hydrogen has one bright line spectrum and helium has its own. Here's hydrogen's and here's helium's, by the way. And if you had a sample that contained both hydrogen and helium, then it would have the lines for both elements in it. So what you can do to represent that is you would just need to combine the spectra for hydrogen and helium into one spectrum, and that would be what you would observe. So I just wrote in that the spectra would combine, but I'm asking also to do a sketch. Mine's going to be in black and white because I don't have all these pretty colors available, but if you have markers or something, feel free to get creative. I'm going to combine the spectra of hydrogen and the spectra of helium in the blank box below. Okay, so I went ahead and tried to show that. So you can see this line is represented here, this line is represented here, and then over on the right, this faint line there, here it is. This line is here, and that line is there. So I tried to represent all the lines in all the places in the second spectrum, and that's what you would expect to see if you had a combination of spectra. So here's the pair up that you should copy down. There is a bit of a long paragraph here. I think I'm going to go ahead and ask you to copy it. It doesn't look too long to me. But don't solve any of this. We'll do this in class when I see you. And here's your summary. Please do include a rudimentary sketch of this and this and this. And they're representing the steps in electron excitation. We'll answer them in class, however, when we go over this lecture.